Log on, tune in, find out. Another good idea from Cambridge.
More about computation.
Thank you very much. And thanks to the organizers for this opportunity to speak here. It's really a wonderful conference. So today I will be talking to you about computational inversion and many aspects of it. And first of all, let me just point out a couple of words about my background. Namely, I've been oscillating between industry and academia. So after my PhD, I worked a while at the instrumentarium imaging, making X-ray devices. Then again in academia in Japan with Masaru Ikehata. And then back to Finland to work for GE Healthcare that bought the company Instrumentarium meanwhile while I was in Japan. And then the dental imaging part was sold and named as Palodex Group. I worked there and then I returned to academia again. So this is kind of an encouragement for all young researchers here. It's really a good idea to spend also some time at the industry to learn about the practical application side of our field. And let me just mention too that I represent the Finnish Center of Excellence in Inverse Problems. We have this team of research groups around Finland. As you see, we aim to cover the whole of Finland with inverse problems groups. So whenever you feel like postdocing in Finland, please contact us. Okay, first of all, let's see what kind of problems are these so-called inverse problems. One of my favorite ones is image deblurring. So imagine we have this sharp photograph, or actually we don't have it. We have misfocused our camera and we have a picture like this. But we would like to see a picture like this. What can we do? Well, the process from this image to this image is quite simple. It's just a convolution by some Gaussian kernel. But the inverse problem would be, how can we come back from the blurred photograph? So the direct problem, if we have the sharp photograph, it's quite simple to compute or construct the blurred image. But the inverse problem is the opposite. When we start with the blurred one, how can we find the sharp image? And although conceptually here these problems seem to be symmetric, we can go either way, actually they are not symmetric. The blurring process removes some information from the picture, and it's much harder to come back from the blurred image to the sharp one. Here I just show you a simple example where I wrote this linear operation, the convolution operation from this picture to this picture as a matrix vector product by writing this image as a vector, by dropping down the columns of the image, multiplying by a matrix will produce this one, and then I just apply the inverse matrix to this image. Here you see the result. Something strange is going on. It's not just invertible like that. Using regularization, which I will talk more about on Friday, it is possible to sharpen the image, but typically only to some extent. Here you see a Tikhonov regularization starting with blurred image and producing this one. It's not perfect, it's not as sharp as the original, but still it's a little bit sharper than this one. This is one example of the results that can be expected from computational inverse methods. Not necessarily perfect, but still better than the blurred image. Here is one practical example of deconvolution. You may know that the space telescope Hubble was sent up to space. It was quite an expensive project. I have no idea how many zeros there are in the number of dollars used in this project. But there it was, and it turned out that it had a flaw. The lens had been very precisely cut to a certain shape. However, the shape was computed incorrectly. There was some minus and plus sign switched at some point. So the images looked like this, quite blurred. Then a deconvolution algorithm was constructed for this problem, really adapted to the shape of the lens and to the particular error that the lens contained. And it was possible to get this kind of sharp images from the Hubble. Then, as you may know, they actually went to space and corrected. They put another correction lens to the telescope. Here they are seen practicing underwater this operation that was done in space, free floating. And after this, the images became very sharp, as you have seen, but actually the same sharpening program could be again used to sharpen even these much more sharp photographs delivered by the corrected lens. Then let's have another example of a linear inverse problem. The deconvolution problem is linear, and so is the X-ray tomography problem. This is actually my model problem I will be talking to you about in much detail later. But in this introduction, let me just mention that in X-ray tomography, the direct problem is that if we know what is inside the patient, what are the inner organs like, then of course we know what the X-ray images would look like. But the actual problem is again the opposite, the inverse problem. If we have available X-ray images from different directions, how can we know what is the three-dimensional structure that produced those images? And this is a widely used technique nowadays, started by Cormack and Hounsfield in the 60s and 70s, and it has been developed a lot since. This is a picture of a modern CT scanner. A person is put here inside. Here's an X-ray source, some detectors, and this whole thing rotates around, and the patient is moved, and depending on the generation of CT scanner in different ways, either slice by slice or maybe using some spiral movements and some reconstruction algorithms, the inner structure of the patient can be seen with the resolution of roughly 1 millimeter voxels. I'll be talking a lot more about this application, but let me mention at this point something about the power of mathematics. The same mathematics that is behind the medical X-ray tomography problem can be seen also in this space-borne measurement problem, where the idea is to map the amount of ozone at different heights in the atmosphere. So here the direct problem is, if we knew how much ozone there is in different places, then we knew how much the light from this star will be attenuated on its way through the atmosphere and detected by this satellite. The satellite is moving, it's recording these lights of one star at different points, collecting actually at different spectral frequencies. And the inverse problem is, if we know these measurements, what was the ozone profile that produced it? Actually, this is the Envisat satellite, which is rotating as I speak. 400 times a day it rotates around the Earth and maps the ozone layer every day. Here is one example of one ozone profile recorded in northern Finland in Sodankylä, and this profile was actually verified by sending up some balloons and some measurement devices that really measured the ozone, and it was compared to the result of the inverse computation. And it's really fun that actually the mathematics of this problem of spatial measurements is the same than in medical X-ray tomography. Then let's move on to nonlinear inverse problems. You heard from Adrian already about this problem. This week it's electrical impedance tomography, where some electric currents are fed into an unknown body and voltages are measured, or vice versa, voltages applied and currents measured. And then the goal is to see a picture of what is inside, for example, a patient here. We could think of imaging the heart and lungs of the patient by having this row of electrodes around here. There are many potential applications for this. For example, I heard from David Isaacson that they had once a collaboration between Rensselaer Polytechnic Institute, where David Isaacson works, and Massachusetts General Hospital, where there was one victim of a motorcycle accident, unconscious, lying in a bed and breathing with breathing machines and kept alive with machines. And they attached these kind of electrodes and this imaging device to her, and they could see in real time how the lungs were filling up and emptying, but suddenly actually one lung collapsed. Only the other one was working anymore. And if a person is conscious and this kind of lung collapse happens, it's very painful, and it's of course immediately detected by the patient herself. However, in this case, this electrical impedance tomography was the only way to detect this very dangerous condition that could lead to some serious inflammation. Here's an example of one of the experiments we made with this problem. This is a kind of a tank containing some salt water. Salt water here in between these objects. So the salt water has conductivity 424. Here is some piece of agar made with salty water so that it has higher conductivity than background, kind of mimicking a heart filled with blood. And here are lungs made of agar and with water having less salt than the background, being like lungs filled with air and not conducting so much electricity. And here's an image computed from the data using the so-called D-bar method, which is based on Adrian Nachman's reconstruction proof from 1996. And we can get images like this from real data. And this is a truly non-linear imaging algorithm that produces this picture. Yet another nonlinear inverse problem about the inner structure of our own planet, Earth. If we knew exactly what is inside, we could predict how vibrations from earthquakes travel through the Earth and what we would measure on the surface. But the inverse problem is actually what we have to deal with. We have data around the world, and then we have to recover what is inside. This is quite a difficult problem, and actually I think nowadays everything that is known, or we think is known about the insides of the Earth, is the result of this kind of inverse process. I think there's a lot of work to be done in this area. It's a fascinating and very difficult problem. And then I'd like to describe a new problem, at least new to me. We started to work on this a couple of years ago. It's called glottal inverse filtering. And here the idea is that when people are speaking, what happens is that the vocal folds vibrate. There is some air coming from the lungs, and with some muscles and quite complicated anatomy in the larynx, we are controlling the movement of the vocal folds. And actually there are kind of two bags of water hitting each other like this, opening, hitting back, opening, hitting back, opening, and it makes a sound like roughly like this kind of sound comes out of the vocal folds. But then the shape of the vocal tract, the shape of the rest of the anatomy here produces sounds and vowels. For example, let me produce for you the vowel but next I will change nothing else but the shape of my lips. Nothing else is changed, I promise. So the went into O. This is how we produce vowels. And here the direct problem is, if we know the vibration signal in the vocal folds and the complete shape of the vocal tract, how to compute what the microphone records here, then it's just quite well-known physics how to compute the signal. But the inverse problem, again, is the nonlinear problem. It's kind of a blind deconvolution problem where both the excitation signal is unknown and the shape of the vocal tract is unknown. So it's quite a difficult problem in signal processing, in acoustics, to recover from the recorded signal the excitation and some kind of parametrization of the vocal tract. And this makes actually a big difference. If we would have a perfect or a very good glottal inverse filtering algorithm, it would have a big impact on technology producing speech, like synthetic speech, like text to speech. If the computer has some text and reads it aloud to make a natural sounding voice, it needs a very good glottal inverse filtering algorithm. This has a big impact for disabled people who cannot speak themselves but would like to express themselves, especially with emotional speech, having some emotional components. Also, good glottal inverse filtering is needed in automatic understanding of speech, recording in some noisy environments in the city somewhere, in trams, recording speech and then making automatically the speech into text. In this kind of problems also glottal inverse filtering is needed. And now I would like to play out some sounds of synthetic speech, where in the first example, I have two examples, and both of those sentences are synthesized with two methods. The first one is just something quite simple, some commercial, very basic technique, and the second one is developed by my colleagues Paavo Alku and Martti Vainio using a much more advanced glottal inverse filtering algorithm. So let's hear these. Actually, I think I had them already here. Yes.
No one tried the challenge. Now they face a right-wing revision.
Stop. Sorry, I cannot control what. Okay, let's try again.
No one tried the challenge.
No one tried the challenge. Now they face a right-wing revision.
Now they face a right-wing revision.
Now they face a right-wing revision.
Sorry, the audio was a bit incorrect. But anyway, you could hear that the other one was very machine-like and the other one was much more natural. This one shouldn't be here. Why is it here? Well, let's hear them.
No one tried the challenge.
No one tried the challenge.
Now they face a right-wing revision.
Now they face a right-wing revision.
So this is a difference that good computational inversion can make in speech technology. Okay, let's return to the talk, and let me just give you one example what is not an inverse problem. Namely, so far we have had these symmetric problems going from some object to another object and then vice versa. I just called the other one direct, the other one inverse. Here's an example where we have the same kind of conceptual structure, but this is not an inverse problem in the sense we think about them in this community. Here we move between a photograph and its negative photograph, and we can go on between these two as many times as we wish. No information is lost. We can just go back and forth. No noise is multiplied. Nothing difficult happens. And this is not actually an inverse problem in the sense we like to think about them. Instead, we follow Jacques Adamard and look at his definition of a well-posed problem. In a well-posed problem, if we have some kind of input and output, first of all, there should be an output for any input, and there should be a unique output for any input, and there should be continuity between the input and the output. And Adamard was trying to capture all problems worth studying by defining these well-posed problems, but in this community we have the opposite view. We think that if a problem is well-posed, it's not interesting. We are dealing only with problems that are not well-posed, which are called ill-posed problems. Let's see what this means in the case of electrical impedance tomography, for example. There the problem is with condition number 3. Actually, there might be problems with all of the conditions, but here I demonstrate the problem with condition number 3, continuity. Namely, here we have two patients, lungs and heart. Here lungs and heart, but here part of the lung is not filling with air for some reason. Pardon the anatomy, this is not very precise, but as a mathematical example, I hope you will accept it. So what happens in both cases is that this is the conductivity. Then I apply a voltage. Here's a positive voltage. Here it goes to negative, and 0 here, and again positive. And at the boundary, I put the same voltage here and here. Inside, we see this is the potential inside, but that's something we cannot measure. We measure at the boundary. So here we have the current through the boundary. So we apply voltage at the boundary, measure current through the boundary. This axis here is the angle around the boundary. And you can see that although there's a quite big difference between these two patients, the data is almost the same. Maybe I just picked an unfortunate boundary voltage. Let's try another. So now more oscillatory. From negative to positive, negative, positive, negative. Again, you see here the resulting voltage inside the solution of the conductivity equation. However, that we cannot measure. We measure at the boundary, and again we measure almost the same thing. So the huge difference here is shown in the data as only these tiny differences. And you can imagine if I add some noise to this data, if there is some kind of erratic behavior in the data, it's quite difficult to find out these small differences and to interpret them as images like this. In this course, I will be talking about a measurement model like this. M is always the measurement and is a vector with k components. Here we have some physics, or actually we have here a model of a physical process of our measurement. F is what we are interested in. We would like to know this physical quantity F, but for some reason we cannot measure the values of F directly. We only have available this indirect measurement. There's this process, this operator A between. It may be linear or non-linear. In this course, the numerical techniques I will present to you will concern only linear cases. So then you can think this is a linear operator A. Epsilon here is a random noise or some kind of error in the measurement. Usually the structure of epsilon is quite complicated. It's a random process. It gives, with each measurement, it gives a new realization. And I will not go into the details with epsilon too much. It depends very much on the application. In this course, we mainly think that we know roughly the size of epsilon. We don't know epsilon, but we know roughly the size of epsilon. Again, epsilon is a vector, a k-dimensional vector in this equation. So now the direct problem would be if we know F, find M. That's the easy part. And the inverse problem is if we know the data, find the F that produced that data. And in computational inversion, our goal is to write computer programs that take as input the data that our machine, our measurement device gives us. We input that, and output is some n-dimensional vector Fn. We need to discretize. The computers can only deal with finite numbers of objects. There's a finite amount of memory, finite number of computational steps. So we have to discretize the unknown F in some suitable way that depends on the application. And the output Fn should be some kind of approximation to F. Typically F is some function defined on some continuous space, and we have to discretize it maybe by some kind of pointwise evaluation, or maybe in wavelet basis, or maybe in trigonometric basis. So some finite representation we need to have for F. And now, because of some of the Adamard's conditions fail in our case, we have to be very careful in writing these inverse algorithms. That's why I have the word noise robust here. We have to deal with Adamard's condition number 3, namely the forward map does not have a continuous inverse. Let me show this in a schematic picture like this. This is the model space X. This is where the F, our objects live that we would like to know. So there is some F living in some function space X. This line here, or this curve, denotes the domain of the forward map A. The forward map takes some F living in this domain of A into its ideal infinite precision data AF. And this curve here is, oh sorry, this should be A. Let's correct it. Okay, and so okay, so this is the ideal data which is in the image under A of the domain of A. But what we have in practice is this M that has some noise in it. So we cannot measure this ideal AF, this infinite precision data. What we usually know is that this M is at most the length of epsilon away from AF, so that there is some disk in the data space with center at the ideal data, and the only thing we know that our data will be inside this disk. But there are several problems. For example, if we try to invert A, it typically happens that this M is not even in this range of A. It's outside the range. So even if A had an inverse, it would only be defined on the range. So we could not apply it to here. So this is a failure of Adamart's condition number 1, existence of solution. If we just try to use inverse of A, we cannot apply it to M being away from the range. Then it also might happen that there would be two different objects here, another, let's say f prime, that would also map to the same point here. That would be a problem with uniqueness with Adamart if we would like to apply the inverse of A to this point. If it had two or more pre-images, which one would we choose? That would be a problem with uniqueness. And then there is the serious problem, Adamart's condition number 3, continuity. The forward map A in inverse problems does not have a continuous inverse. And continuity is of utmost importance because data always has noise in practice. So whatever inversion we make, it must be continuous with respect to the data. So if you look at the tradition of regularization theory in inverse problems, we actually know what we should do. We should construct a family of mappings, a gamma alpha parameterized by regularization parameter alpha, which is a positive real number. This gamma alpha, for any given alpha, it is a continuous map from the whole space Y to the space X, and for a given F and M, it should in a controlled way give a nice approximation here. And let's see the definition from Andreas Kirsch's book, definition of regularization. So let's see what we have to do. We need to construct a family of continuous mappings, continuous from Y to X, called a regularization strategy. And the regularization parameter that parameterizes these maps this should behave like this strategy. If we had the ideal infinite precision data, then when we, at the limit when the regularization parameter goes to 0, we should get the exact reconstruction back. So this is kind of a basic requirement for the, unless if there is some, if A has some kernel, then we have to deal with some quotient spaces, but let's not go into that. So for a fixed f in x, we should get back from infinite precision data, we should get the correct reconstruction back in the limit when the regularization parameter goes to 0. But then the more interesting case when we do have some noise, epsilon. Now, well, here this should be the size of epsilon. Well, we have some positive size of epsilon. We should describe how to choose alpha as a function of the noise level in such a way that, first of all, when the noise goes to 0 in the asymptotic limit, when the noise vanishes, alpha should go to 0. So in that case, we would get the perfect reconstruction from this condition. But then we need to control the error in the reconstruction in this sense. Notice that this here is the error in the reconstruction. This guy is the reconstruction from the data M, and this is the actual object that produced the data. So we measure the difference of these guys in the norm of the model space X. So this norm here should go to 0. The sup of these norms should go to 0, and the sup here is taken over all data that are at most epsilon away from the infinite precision data. It's kind of a technical definition, but we have to do something like this to kind of invert the non-invertible map A. This is something we need to do with every practical computational inversion method. They always have to be regularized. That's the most important property of a computational inversion method. It has to be robust against noise. So now, if we are faced with some particular application and we want to make a computer program that gives useful reconstructions from data, we have to consider at least these things. How to discretize this unknown f? Typically, the data comes from some physical object that lives in continuum space, and we have to recover some kind of approximation to f. And it depends quite a lot on the application what would be the best way to discretize it. Also, the literature is nowadays full of different regularization methods. Which one to choose? There are many aspects in this, but I think it's important to realize that it depends on the application. The method should produce noise-robust reconstructions that are useful for the end user in that application. So it's not purely a mathematical question, it's a question intimately related to the application in question. Also, in practical cases, we have to think about how quickly we can compute and with what kind of computer we can compute these things. For example, I will be talking about dental X-ray imaging, and dentists, in some things they do in X-ray imaging of the teeth, they need the result in few minutes. They are used to have it like in the time that film gets developed, few minutes. And whatever inversion method we make is useless if it takes more than 5 minutes to compute. It's just not needed in that application then. But on the other hand, for example, in screening for breast cancer, for example, enhancing mammographic images, there usually the situation is that the patient is imaged at one day and the image is read maybe the next day, and later the patient has a meeting with her doctor discussing the image. So then there might be a day or several days for computing, and then there are more options to choose what kind of computer to use, or maybe use a more demanding algorithm. So these, it's the same thing than here. It depends on the application, what kind of reconstructions are needed and how fast. These are important considerations in computational inversion. And when designing this course, I thought that these would be the most important goals of what I'm discussing here. First of all, I would like to show you some examples how to arrive at this measurement model given a kind of practical inverse problem, how to construct this matrix A and choose what these objects are like and the dimensions of them. Then when we also have to discretize F, so that means that A becomes a matrix in case of linear inverse problems. Then I show you how to use singular value decomposition to see from the measurement matrix A whether it really represents an inverse problem, ill-posed inverse problem or not. And then if it does, if it's really an ill-posed inverse problem, how to implement some regularized inversion methods with MATLAB, and I will discuss truncated singular value decomposition, Tikhonov regularization, and total variation regularization. There's not very much time, but I will describe as well as possible these methods, and I will show you numerical examples as we go, how they work, and I will provide you with all the code and examples so you can go on and try them out yourselves later. And also an important topic is the so-called inverse crime. Unfortunately, in many articles and many conference talks, it seems evident that an inverse crime has been committed. And let me explain what it is. When developing a computational inversion method for practical data, it's usually a good idea. In my opinion, it's a good idea to first write a code that simulates the data as well as possible. So then you can test your methods with simulated data first, before applying the method to real data. The reason is that if you start right away with real data and out comes some kind of strange rubbish, that always happens first in computational work. Whatever you get first out is something strange, and there are some errors and bugs and something. So then if you just have the real data and you apply, how can you find what is wrong? It's very difficult. But if you have simulated data, then you can control every aspect of the computation. You can control how to simulate data, and you can find out where the problem is, at least much more easily than going directly to real data. So I recommend working first with simulated data, although it's usually a big work to code the simulator that simulates the actual data well enough. But in any way, it really is a good idea to build such a simulator, but then there is the danger of inverse crime. Inverse crime happens when you simulate the data, and then if you use the same simulation, same computational grid, and the same model in your inversion algorithm, then sometimes happens that you will get very nice reconstructions that look beautiful, but this is not reality. It's just because you are using the same model, something in the computer goes exactly the opposite, and unrealistically good reconstructions come out, and the method will not work at all with real data. Immediately when there is some noise, everything breaks down, but with simulated pure data, it works fine. It's very confusing, and the resulting algorithm is typically useless. So it's important to simulate your simulated data with a different model, at least with different parameters, but preferably with different computational model than you use in your inverse algorithm. That's very, very important, because then you can, if your inversion code works with data simulated with a different model, then you can know that the method will work more probably also with real and noisy data. Okay, let me just advertise a little bit. We are preparing a book with Jennifer Mueller, my longtime colleague. We are writing a book on this topic, computational inversion. In this course, I will be talking about part 1 of our book, which is linear inverse problems and methods for them. But in the book, we also have a lot of stuff on nonlinear ones. I remember Slava Kurilev suggested to change the title linear and nonlinear inverse problems, which means, of course, all inverse problems with and without practical applications. But although this suggestion is really beautiful, I think we made the agreement with Cyan with this name. With and without. Oh, that's right. Yeah, for another. Okay, that's. Yes, thank you, Slava. Excellent. Okay, so I think it's a good time to stop here, and we'll return to this topic later today. Thanks.